Imagine you were hired by the Mall of America. The first task they gave you was to find the entire square footage of every nook and cranny that the mall has. How would you go about doing that? You would probably use the basic concepts from our Chapter 5 unit: right triangle trigonometry, law of sines, law of cosines, and the new area formula. These concepts would be vital in finding a total square area of an object or a shape. That's what your Chapter 5 project is going to be about. Ultimately, you're going to be picking your own shape or building or area to analyze using technology. But before we do that, we need to talk about some basics of different shapes and polygons and how would you go about finding areas. So our first warm-up is this. It says draw line segments so that the polynomial is divided into triangles. And do you think this is possible for any polynomial? Remember, a polynomial is just an enclosed shape with sizes up to 3, 4, 5 on to infinity. If we look at this one right here, this is a pentagon. To draw line segments that divide it into only triangles, and I want this triangles that don't overlap, how might you go about doing that? Well, you could start by going from this one vertex to the other, from here to here, and in doing that, we just created 1, 2, 3 different triangles. Now, if we go over here and look at this 7-sided object, which is called a heptagon, we can do the same thing. I'm going to start by connecting these two vertices, and then these two, the next set, and the next set. In doing that, we've just created for ourselves 5 different triangles in here. So we can clearly see that any polygon can be made into only triangles. This is beneficial for your project because we could use right triangle trig, law of sines, and law of cosines to help us find any missing angles or side lengths. Then we can use our area formula and compute the complete area of these objects. Let's look at some other examples. On this one, they want us to try dividing the following polygons into triangles again. So to do that, one thing you could possibly do for this object is you could go from here to here. You could drop down here to get a triangle. You could also go here, and maybe you wanted to do that. So in doing so, we've just created for ourselves, again, 5 different triangles, and that could be helpful in preparing for our project. If we look over here at this arrow, this one can be done in about 3 different triangles. We could drop right here, and we could also go here, and we'd have 3 different triangles, and we could use our triangle formulas to find the areas. So let's get started about the project. Just remember back when you were younger, before geometry, you always found the area of shapes. You would either draw shapes on grids and count how many squares there were. You would use area formulas, things of that nature. So we're going to actually go back to how do you find the area of any type of shape that you have by building polygons. And some of those polygons could be built out of triangles. So here's your goal. Your goal is to find an area of land, a house, a building, anything on Google Maps, anywhere in the world that you're interested in finding the total area of. Once you've identified what that shape is going to be, or that plot of land, then you want to start thinking about how would you find the total area of it. There are some requirements that you have to make sure that you hold yourself to. One of the first requirements is that you must use law of sines and law of cosines uniquely at a minimum of 5 times in your project. Additionally, you must use the SAS triangle area formula. That's the new one that you learned in class for Chapter 5, a minimum of 5 times. So you have to find the area of at least 5 unique triangles. Now, when you find a shape, make sure it's complex enough. But it doesn't have to be too complex. You're just looking for some triangular shapes that would pop off the page. If you don't see any triangular shapes, but you really love the object you want to do, you would have to force some triangles to happen so you can meet this requirement here. When you are all done, I do want you to present this somehow to me. It's not a formal presentation, it's just something you turn in. And when I say presentation, it doesn't have to be a Google presentation or a PowerPoint. It could be. You could do it on paper, you could do it on tagboard, you can do whatever you want. You will officially turn in something just on Schoology so I can do the grading of a rubric within the system itself. Remember, a picture's worth 1,000 words. This is an activity about finding the area of a diagram. and I can't understand it without pictures, so you're going to really rely on your picture for that. The tools to use, I highly recommend Google Maps to use for that. You could also use Wolfram Alpha. This is a good site, maybe GeoGebra or Protractors. I'm actually going to show you, though, in this document how to use Google Maps to do the measuring and finding areas, which is quite helpful. The last thing I'm going to do is just give you some advice about helpful hints. When you use Google Maps, you're going to use that to help you find lengths of different sides. It will tell you that. It will also tell you the area. You are going to have to find the area of the entire shape. However, you must show all the supporting mathematics to compute the areas. Google Maps is incredibly powerful, but I want you to be able to show me why and where Google Maps is getting triangle areas, areas for rectangles, areas for trapezoids, things of that nature. You can find areas for any polygon shapes or circles. They do not have to be made up of all triangles. Again, your project is a minimum of 5 triangles. If there's rectangles or squares in there, absolutely just keep it simple and find the area of those. Your 5 triangles you find must be unique triangles. You have to use the new triangle area formula of 1/2 AB sine of C. And again, don't forget to show law of sines and law of cosines being used at least 5 times. Your presentation too, be thoughtful in that and make sure your presentation is detailed enough that I can follow your work and that you can get a good score on your project. This here is a scoring rubric that will be used. It says here from 4 to 1 points, but on Schoology the grading would be 1 point, 3/4 of a point, 1/2 a point, and 1/4 of a point, which would then total for a maximum of 5 different categories. 1 point each would be a 5-point project in the summative category. This first one should not be hard to get, your accuracy of measurements. You need to have reasonable measurements for every single side length on your object, and it should be labeled on your picture. Google Maps will give you this information. The formula requirements. Are you meeting that there's 5 uses of law of sines, law of cosines, 5 uses of the area triangle formula? The next criteria is your mathematics used. Are all accurate and appropriate formulas being applied where they should be? If you have a trapezoid, are you using the formula for a trapezoid? Are you doing it accurately? Are you using the right law of sines or law of cosines when you should? So just be thoughtful on that. The explanation or procedure used, completely and clearly and logically explain how the total area was computed. It's not going to be hard to get lots of shapes to have to find for your object, so you need to show me how it's all being pieced together. And then finally, I will give you a score on how well it's presented. Can I follow your work? Is it easy to see how you're coming up with things and coming up with totals? So you might ask yourself, what are some appropriate objects or shapes or buildings to look at? I particularly like the Mercedes-Benz, so I looked at the Bloomington dealership, Feldman Imports Mercedes-Benz. This building, to me, when I first looked at it, the bottom half here is definitely a quadrilateral or a rectangle. Very easy to find the area. But I noticed here in the various showroom windows, they're going to have some various angles where I could compute and come up with some triangles. So I would say picking this Mercedes dealership for your project would actually be an adequate shape with enough complexity. These side windows on the showroom are going to be quite a bit of work, but it is very reasonable. Another potential thing, maybe you want to look at the area of South Dakota. If you want to show me how to measure that. You're going to notice, obviously, this side of the state is very rectangular and very basic. However, when you get over in this area and in this area here, it's going to be much more complex to do, so you will hit some trickier spots. That would be a reasonable project. What about finding the area within target field? Maybe you're going to look at just the inner field here. Maybe you'd look at the building. Would that be adequate for a project? At initial glance, I would say probably. This corner here looks like it might be a little more detailed in terms of having an angle, something more like a triangle corner, so that could be difficult. That would be something we want to investigate a little bit more if there's enough complexity in it, because you need to pick objects that have a little bit of complexity. If they're too simple, they're not going to count. What about Hilltop Primary School? I went on Google Maps and here is the image of that. I will tell you, in my opinion, this is actually a very complex project with lots of angles and corners. And this might be too complex to actually deal with. The reason is this location here is a major polygon where you could sector it off into a variety of different triangles or different types of polygons, which could be quite complicated. This area here obviously is not difficult with a rectangle, but these other portions might make it too hard to do. Another school, I looked at Dassel Middle School, and their high school's connected. This one, unlike Hilltop, is much more linear in terms of their line structure, but I really like this corner here, you kind of see that triangular portion. You also see a little bit of details and complexity in there. This is a pretty big building, but it's something you could look at. What about Lord Fletcher's on Lake Minnetonka? When you first look at the overview of this, it is very linear and rectangular and would be easy to do in terms of rectangles. Now I have to caution you, picking a shape like this may not be complex enough unless you add some complexity to it. I could easily partition this off into just rectangles and probably get this project done in 15 minutes, and that's not the intention. The one requirement here is you do need to be using the rectangular shapes. So if you were to do something like this, you'd really have to partition it off into some more complex triangles. So you're using law of sines and law of cosines. I would venture to kind of stay away from something that is too simple in nature like this, which is made up of all rectangles, because you're going to have to make it more complex. What about the Xcel Energy Center in St. Paul? I think the Xcel Energy Center actually has some really nice details. This right here, the doorway entrance would be involved. You could kind of ignore all the seats and just look at the outside framework of the entire Xcel Energy Center. So that would be an interesting one to try. If you're into the arts, how about the Walker Art Center? I tried looking at this one and I thought, it was very streamlined and somewhat simple, but I liked, for example, this corner wasn't too bad. It might be a little too simple still. I'd have to think a little bit more about the Walker Art Center. Because it is almost just very linear and not a lot of complexity in the building itself. What about the Highland Ski Area building over in Bloomington? This building right here could be complex enough. On the front end right here, very rectangular and not hard to do at all. However, as you get into this location right in this spot, you may be able to find enough triangular work happening. Also, possibly right in here, you're going to encounter some triangles. So this could be a good project. Caribou Coffee here in Mound. This is the outline of the Caribou building. Again, this might look a little simple at first, but I could possibly see maybe having enough angle information in here or here to get some triangles. You really want to be thoughtful, though. This may not be complex enough unless you add some more complexity to it. Now, once you find your object, you want to start getting the measurements of all the sides and figuring out which shapes you're going to create, such as squares, rectangles, and triangles. I'm going to go back to the Mercedes dealership in Bloomington and show you how I'm going to approach this corner display window and get a measurement. You can do this all within Google Maps. So in step 1, when you're in Google Maps, just right-click, and when you do that, you want to select down here, it says Measure Distance. After you do that, it's going to change so that you click and drag the segment as you need to get your first measurement. So you're going to notice after I did the measure the distance, I clicked on the screen and I got this segment, so I dragged it to get this measurement. What I'm trying to do is actually create a triangle for this region here. So when you do that, notice right here it actually shows the distance is 48.87. So I'd want to record the length of that in feet. And that's what step 2 talks about. Now, step 3 says to get a second segment and drag it where needed. So just click one more time. When you click again, another segment's going to get created. I needed to get this little part of the window frame, so I just dragged it from there. Now you have to be careful because at this point, when you look at the screen, what it's going to show you is the distance right here says that the distance is 58.47. That's the total distance of both of these segments. So to figure out the distance of this little segment, I'm going to take this total distance of the 58.47 and subtract the first distance of our longer segment of 48.87. And when you do that, you're going to get that the distance of this little line segment here, I have stated, is 9.6 feet. So then I would label that measurement also. Now, step 4, get a third line segment, and we're going to try to connect from here to here. So in my step 4, you're going to see the next picture. I did create the third line segment from here to here. Now, if you look at the screen at the total distance, what it's going to state is it's going to have the total distance down here, and it's going to say it's 105.85 feet. So to figure out the length of this third segment, just take the 105, subtract out the total of the two segments, and you're going to get 47.38 feet, which means this third segment is that length. Now, after you have all three measurements, you are going to notice in step 5, it talks about here, it actually tells me the total area. So I know the area of this triangular region is 227.06 feet squared. Now, you'd think the project's done the work for you, but it hasn't. You need to show me the mathematics behind that. You cannot assume this is a right angle anywhere. You must find one of the angles. The only way to find one of the angles is to actually do law of cosines to find the angle. And then you would go do the 1/2 AB sine of C formula. So let me show you, and I'm going to set up the law of cosines for this triangle here. So notice the formula I chose to write is this one here. I'm going to take this side length here and find its matching angle. So the angle here and this side length here match up. So remember to write law of cosines. I'm going to start with this side length here and square it. I'm going to add to it the other two side lengths squared minus 2 times each of those side lengths. And then I'm trying to find what I'm calling angle A. And angle A is my red one. Once I do the math, I'm going to ultimately get the measurement of angle A. And I'm going to get what the value is for that. So this is going to be in degrees. Then the last step is I need to actually figure out how did they get the area of 227 feet squared for this. All you have to do is you can go in, remember, and use our formula. The side angle side formula is 1/2 AB sine of C. Now, for me, I'm choosing my two side lengths as this side length, and this angle. So you always choose the angle related to the two side lengths you have. So for this formula, all I have to do is I'm going to come in here and I'm going to keep it as 1/2. Again, the two side lengths I'm using are this and this, so I'm going to write it as 48.87 and then 9.6. Now, don't forget the word sine. That makes it very important. And the angle I have to use right here is because I chose these two side lengths, I use the angle created by that. So for me, whatever I found this angle measurement was, goes in here. So in my calculator, when I go ahead and I compute 1/2 times this number, and the sine of the angle, it should be incredibly close to, if not the exact same number that Google Maps computes. Now this is the work you have to show within your project. And don't forget, you have to show law of sines and law of cosines a minimum of 5 times to get your angle measurements. In addition, you have to show the side angle side area formula 5 times for at least 5 triangles. Show the work in between here to how you got the angle. Just don't jump from the formula to the angle measurement. Do the actual mathematics, because that's what I'll be grading. So if you're looking for some advice on how to get started, what I first did is I printed off my object here, and mine was, again, Feldman Imports in Bloomington. And then I took a ruler and I just drew all the shapes that I would be finding. And what ended up happening, there are 11 shapes in total. I have 4 triangles here, 3 triangles here, 2 trapezoids, and then I wrapped up with 2 rectangles. So then I would take my shape here and then I'm going to go into Google Maps and do all of the measurements. So I'll do the measure distance tool, I'll get the lengths for this segment, for all these segments, and I'm going to measure and label every single segment in this drawing with a measurement. So then after I've done that, how might I piece it together? You know, I identified all the shapes I needed. There's 11 shapes. I realized, again, there's 7 triangles, 2 trapezoids, and 2 rectangles. So then maybe I just dive into the math on how to find the areas. The trapezoid and rectangle, I'll just review from geometry how to do that, and I should hopefully have enough information, or I may have to get a little bit more information for my trapezoid. But for the triangles, remember to find the area. It's the 1/2 AB sine of C. So you need the sign of an angle. So you have to find at least one angle in each triangle, which means you're required to use law of cosines, as I talked about already. Once you have at least one angle, you have two side lengths, so you can find the area of the triangle. Within the work that you present, some other things again to keep in mind. You must show the area computations for all the shapes that make this happen. Show the formula that you're using and the necessary math to solve, and then give the total area of your object. And don't forget the unit of measure. How did you measure it? Inches, feet, what have you. Again, friendly reminders using law of sines and cosines at least 5 times, the triangle formula 5 times. And think about how you're going to organize and put this together and turn it in so it really flows and it looks good. Good luck with your project. Have fun.